This session we describe the exponential growth and decay equations, an application of first order ordinary differential equation. So the natural growth equation is given by dy dt equals to ky, where k is a constant so when two cases, one, when k is positive, then we have an exponential growth. But when we have k is negative, then we have an exponential decay. So the number k is called the rate constant or growth constant and has units of the inverse of time. Inverse time, so number per second, or it may be number per minute or number per week, number per day, number per year. So a reason as to why we are calling this the value of k positive and negative, either exponential growth or exponential decay, is because with this differential equation, we can solve this one. So if we let the value of y at t equals to 0 to be y naught, then separating variables will have dy over y equals to k dt, integrating both sides, we get integral of dy over y equals to integral of k dt, which gives ln of y equals to kt plus c. And now exponentiating both sides, y will be e raised power k t plus c, which is e raised power c, e raised power kt by loss of indices, which is C1 e raised power kt. C1 is e raised power c. So that y of t is given by C1 e raised power kt. But when t is 0, we get y naught, which will be C1 e raised power k times 0, which is just C1. So this means y naught equals to C1, and therefore y of t is simply y naught e raised power kt. So this is the solution. So you see the solution has an exponential function. So that's explain why we have exponential growth and exponential decay, depending on the value of the constant k. So we can have some sketches here. T, y. So we have this, and then we have this. It's like we have so this is when e raised power kt, k positive, we have growth, and e raised power kt, k negative, we have decay. Remember, this is how the graph of y equals to e raised power k t behaves for k positive, and k negative. This is how the graph looks like. Y equals to e raised power kt for k negative. So this is a single graph showing growth, and this is a single graph showing decay. Note that in the case when k is negative, the natural growth equation can also be written as so dy dt equals to negative ry, where r is the absolute value of k is positive. In which case, or in this case, the solution has the form y of t is given by y naught e raised power negative r t. So that's how we can also describe it. So some key things are population, or bacteria can be modeled using the equation dp dt equals to kp. They're the same as what you have written as the natural growth equation. Number 2, actually whose solution is P of t is P naught e raised power k t. It's not very hard to get that solution by letting P at 0 to be P naught. Number 2, sample of a radioactive isotope can be modeled by the equation dm dt equals to minus rm m at 0 equals to m naught. So which implies on solving m at t is m naught e raised power negative r t. So the next session we will be doing examples to illustrate how we solve equations on growth and decay. Thank you.